Hello, my name is Bill Robbins. Today I'm going to talk about two topics associated with junction field effect transistors. First, I'm going to talk about power junction field effect transistors, and then secondly I'm going to talk about a related device, the field control thyristor. JFETs for power electronic applications normally are not used when we're talking about silicon-based JFETs, mainly because they have a normally on characteristic, which is not desirable. Normally off JFETs can be made in silicon, but they need extra design in their drive circuits, which complicates the overall design of your converter. Silicon-based MOSFETs have better properties and are normally off, and hence are used in preference to the silicon-based JFETs. However, JFETs do not require a high-quality gate oxide or insulator, such as SiO2 on silicon, whereas MOSFETs do require a high-quality gate oxide or insulator. This is a distinct disadvantage when we are talking about making these power devices in wide bandgap materials, where the lack of a high-quality insulator limits the fabrication and performance of MOSFET-based devices. Power JFETs have been fabricated in silicon carbide and are now commercially available, and they are competitive with silicon-based IGBTs. Here I'm showing the cross-sectional area of a N-channel trench gate MOSFET. This device is called a trench gate for obvious reasons, namely the trench which is etched in this area of the device. The fabrication of the device is done by first taking a wafer that's been heavily doped N-type, growing a lightly doped N-type epitaxial layer, which will be the drift region, and then doing the P plus diffusion for the gate region, and then finally the N plus diffusion for the source. After that is done, then the trench is etched, as I've indicated, and finally the metallizations are applied. The gate source regions are highly interdigitated. There are probably thousands on a given device. Typical spacings from one source to the adjacent source is a few tens of microns. The dimensions of the gate and channel perpendicular to the page are hundreds of microns. The drift region thickness, in particular right here, is determined by the breakdown voltage rating that the device is designed to have. And again, I'll call your attention to the fact that there is no gate insulator needed for this device. Over here on the right I show the circuit symbols for the power JFET. It's the identical one that we use for signal level JFETs. For the N-channel device, it looks mostly like a MOSFET symbol, except for the fact that the gate lead points directly into this vertical line on the MOSFET part of it. And the arrowhead pointing in indicates it's an N-channel device, because if we forward bias the gate source junction, we will have a N-channel device. The P-channel device symbol is identical, except the arrow is pointing outward, indicating you have to bias the gate source junction, as I've indicated here, in order to affect the operation of the device. Going on to the next slide, I'm going to talk about first the normally on state normally off device. In order to be normally off, what that means is at zero bias between gate and source, we have to have the channel blocked off, and that's what I'm showing right here. In order to do that, the channel width, which is the dimension that I've indicated on the drawing right here, has to be fairly narrow, on the order of only a few microns to perhaps 10 microns, so that the zero bias depletion layer width between the P plus diffusion that forms the gate and the N minus channel region reaches halfway across the width of the channel in this direction, and on the opposite side it reaches across here. If that happens, then the channel is completely depleted of carriers, and hence we have a blocking junction. As you apply more and more drain to source voltage, the depletion layer that is in the channel begins to grow toward the drain, as I'm indicating here and is already indicated on the drawing. To turn the JFET on, what we have to do is shrink back the depletion layers, and that is done by forward biasing the gate source junction, which causes the depletion regions, as indicated in the drawing and as I'm re-emphasizing here, back toward the metallurgical junction. This opens up the channel, and then current can begin to flow from the drain to the source, as I've indicated here. One has to be careful about how large the voltage between the gate and source is, because if you exceed on the order of a silicon device on the order of about 0.7 or 0.8 volts, you're going to strongly forward bias that gate source PN junction, and you will have significant gate currents flowing. The drain current will saturate and flatten out, becoming independent of the drain to source voltage in this device as it does in a MOSFET, for the same basic reason, and that is electron velocity saturation. Going on to the next slide, I show the characteristics of the normally off device. On the left we have the output characteristics, and if you exceed about 0.7 of a volt for the gate source voltage, you've exceeded the threshold voltage of the normally off device, and as we've already indicated, the channel is now open and you begin to have current flowing between drain and source. And the larger the gate to source voltage is, as we go up in this direction, VGS1 less than VGS2 and so on, the larger the gate to source voltage above threshold, the wider the channel becomes and the more current can flow. You have to make sure that you do not exceed the breakdown voltage rating of the device, otherwise it will go into avalanche breakdown. The transfer characteristics are very similar to those of a MOSFET. Once you exceed the threshold voltage, the current, pretty much the drain current, becomes linearly proportional to the gate to source voltage. However, I want to re-emphasize there's a fairly narrow range of allowable gate to source voltages to turn on this normally off JFET. In silicon, it's on the order of about 0 to 1 volt. In silicon carbide, because of the larger bandgap of the material, the range is about 0 to about 2.2 volts. If you exceed these maximum gate to source voltages, the gate to source junction then has become strongly forward biased and you have substantial gate current flow, and you are injecting from that PN junction excess carriers into the channel region, and you've entered a new mode of operation. Basically it becomes an analog to a bipolar junction transistor, but it is not a well-designed bipolar junction transistor, and so it's something to be avoided. Now I'm going to go back and talk about the operation of the normally on JFET. In the normally on JFET, the channel is completely blocked off at 0. It's completely open, just the opposite. I'm over here on the right hand side, where the JFET, when it's normally on, when you have 0 bias between the gate and source, the depletion layers are shrunk back against the metallurgical junction, and essentially the complete channel width is available for current flow. And so current in the on state flows as I've indicated here, and that will occur when you have 0 gate to source voltage. Now, in order to turn the device off, we have to grow these depletion layers in this direction so that they will eventually meet in the middle, and that's what I'm showing over here on the left hand side. If you exceed what is called the pinch-off voltage, right at the pinch-off voltage, which is a negative voltage between gate and source, the depletion regions have just met in the middle of the channel, and thus depleting the entire channel of excess carriers, of any carriers, and so no current can flow. If you make the gate to source bias even more negative than the pinch-off, you are making sure that you are overdriving it and ensuring that the device is off. As you increase the drain to source voltage under those conditions, the depletion layers grow, as we've already indicated and as I'm re-emphasizing here with these arrows that I've just drawn. Again, the output characteristics for this device are very similar to those of the normally off JFET. When the device is conducting, in the active region, the drain current is pretty much independent of the drain to source voltage, except now The largest current flows when you have zero gate to source voltage, and as you go negative, as I'm showing here, the current becomes less and less until you reach the pinch-off voltage. At the pinch-off voltage, when the gate to source voltage is more negative than the magnitude of the pinch-off voltage, the device is off. The transfer characteristic is shown over here. At zero gate to source voltage, you have the maximum current, and that's usually a parameter given on a specification sheet. It's usually called IDSS, meaning drain to source current when the gate is shorted to the source. When the gate to source voltage exceeds the value of the pinch-off voltage in the reverse direction, then the current is zero, and for any larger gate to source voltages in the negative direction, the device stays off. The switching characteristics of a JFET are very similar to those of a MOSFET. The equivalent circuits in the cutoff and active regions for a JFET are identical to those of the MOSFET. We have the gate to drain capacitance, gate to source capacitance, and then a dependent source that represents the static operation of the device. The current source is zero in cutoff, and in the active region, the current is proportional to the gate to source voltage. When the device is in the on state, we have again the same equivalent circuit as for a MOSFET. We have a gate to source and gate to drain capacitance, and an on state resistance, which is going to be quite low. The switching waveforms are nearly identical in the same circuit as those of a MOSFET, and so I won't discuss them in any detail. The values of the switching times for a JFET are very similar to those of an equivalent MOSFET in the same circuit. If you need more details, I would refer you back to the video on MOSFETs to review those waveforms. The next consideration is the on-state losses of a JFET. Here I show the cross-sectional view of the JFET, and the two principal components of the on-state losses are the drift region resistance here and the channel resistance. If we exceed about a few hundred volts ratings in the JFET, then the drift region resistance is the dominant component of the on-state losses. And this is very similar to that of the MOSFET. MOSFETs and JFETs that have functionality that are equivalent to each other in terms of breakdown voltage and current will have very similar on-state resistances, and thus on-state conduction losses. The switching losses of the JFET are going to be very similar to those of an equivalent MOSFET because they have similar switching times. The next device I want to talk about is the field control thyristor, or FCT for short. Here I show a cross-sectional view, and you'll notice it looks very, very similar to that of a JFET with one important difference. Instead of an N-type heavily doped region next to the anode, we have a P-type region that's heavily doped, and thus we have an injecting contact. This P plus N minus drift region is the P-N junction where we inject the excess carriers, and I've explicitly called out here that injecting contact, which is the unique feature of the FCT. This device is sometimes known by the name of bipolar static induction thyristor, or BSIT-Thy for short. The circuit symbol for the FCT looks like that of a diode, and we have a gate coming in, and we show an arrow indicating that you can turn the device on by injecting current via a positive gate to source, or a gate to cathode voltage. I'm showing here what we would call an N-channel field control thyristor. It's possible to make a P-channel device, but in most situations, as with other power devices, we prefer the drift region to be N-type because of its lower ohmic resistivity. The FCT characteristics look somewhat different than those of a junction field effect transistor. The anode current as a function of the anode to cathode voltage looks more like those of a vacuum triode. or the triode region of a MOSFET. In order to have the device off, you must apply a gate to cathode voltage, and you have to increase that gate to cathode voltage to hold off larger voltages. And you'll recall that we have to have a negative gate to cathode voltage. The transfer function, anode to cathode voltage as a function of the magnitude of the gate to cathode voltage, is fairly linear, and the slope of that is called the blocking gain mu. And typical values of that blocking gain can be as large as 100 or more. We could make the device normally off, but that would increase the on-state losses compared to the normally on device, and so it's not likely that you're going to see commercially available normally off FCTs, at least in the near future. Going on to the next slide, the physical operation is already probably fairly clear. I think I've alluded to it already, but let me go over it briefly. The FCT is essentially a power JFET with an injecting contact. The injecting contact causes conductivity modulation of the drift region and thus reduces the conduction losses to a significant degree. At turnoff, we have to draw large negative gate currents similar to that of a GTO because we have a lot of stored charge in the drift region. However, the FCT is not a latching device. The FCT has no regenerative action like a GTO. That means that in order to keep the device on, you must keep the device gate to cathode voltage large enough, it has to be at 0 in order to keep it on. And in order to turn it off, you must keep a negative gate to cathode voltage larger than the pinch-off voltage in magnitude. Although it's possible to make a normally off device, it isn't going to probably be practical in the near future, at least, because it requires narrow channel width, and the zero bias gate depletion layer has to pinch off the channel, and having a narrower channel width means probably higher on-state losses. Over here on the right, I show a convenient way of driving the FCT on and off. It's basically what we call a cascode switching circuit. I have the FCT connected in series with a low voltage high current MOSFET. If the MOSFET is on, then we have the source nearly at 0 potential. The gate is already at ground, and so we have essentially a 0 gate to cathode voltage, and so the device will be on. To turn it off, we turn off the MOSFET. That allows the voltage of the cathode to rise above ground, probably significantly higher than the gate voltage, which is at 0. To keep the voltage across the MOSFET from getting too large, we use a voltage divider, as I've indicated here, so that we keep the drain to source voltage and hence the cathode to ground voltage under control. We would typically like to use a low voltage high current MOSFET, so we're talking about probably no more than a 50 or 100 volt rated MOSFET. To avoid large currents flowing down here, the resistors R1 and R2 would probably be in the megohm range or more. The FCT switching characteristics are going to be similar to those of a Thyristor or GTO, including the need for large gate currents at turnoff. The gate control turn-off and turn-on characteristics of the FCT are similar to those of the GTO, except the switching times are going to be considerably shorter than those of a GTO. The gate drive has to be applied continuously because the FCT has no latching action as the GTO or Thyristor does. The FCT is going to have a much larger reapplied VDT rating than the GTO because of the lack of this latching action. So if the FCT is reverse bias and you want to turn it into the forward blocking state, you can have that rate of reapplied voltage significantly larger than that for a GTO of comparable performance. The FCT will have dIdt limits, as does the GTO, because of localized turn on and then expansion of the conducting region across the entire device cross section. Finally, to compare in a general way JFET devices with other power devices, blocking voltage capabilities of the JFETs are comparable to MOSFETs. In fact, there are 1700 volt rated JFETs commercially available at the present time, which is in the 2014-2015 time frame. The JFET on-state losses are comparable with MOSFETs. The switching speeds of the JFET are comparable with MOSFETs. The silicon carbide JFET is commercially available at the present time, again the 2014-15 time frame. And the JFETs are easier to fabricate on wide bandgap materials than MOSFETs because it does not require a high quality insulator. This may change as the technology in wide bandgap materials improves and we find a high quality oxide. And if that happens, then probably MOSFETs will take over from JFETs. I think this is a adequate summary of junction field effect power devices and the related field control thyristor. So I will end this discussion at the present time. Thank you for your attention.